Hello, this is Dr. Gardner. Today we're going to be looking at how to recognize chemical reactions. Now this is a wonderful tutorial to follow up right with our tutorial on balancing chemical equations. So I do recommend you maybe watch both of these tutorials on the same day. Now, in order to recognize chemical reactions, I am expecting you've watched our previous tutorials on how to write and read chemical formulas. I also expect that you've listened to our tutorials at the beginning of this course on the law of conservation of mass, which we'll be seeing occurring again in this tutorial as well as in the tutorial on balancing chemical reactions. I also expect that you've watched our tutorials on physical and chemical properties and how these relate to mixtures and chemical reactions. I also expect that you understand phase changes as we go between solids, liquids, and gases when we discuss these tutorials. Now, we will be developing a few new skills today. We'll be looking at how to define a chemical reaction, what type of properties we look for with respect to the changes in chemicals and substances in a chemical reaction. We'll also be looking at a short review on the law of conservation of mass with an example reaction. And then we'll be looking for other clues that we can look for that indicate a chemical reaction has occurred or a chemical change has occurred. So first of all, how do we know what a chemical reaction is? Well, first of all, a chemical reaction would be the conversion of one substance or a set of multiple substances as reactants into another set of substances, which we call products. So we're looking at this change in the substances we begin with. If you end up with new substances at the end of the chemical process, then you know it is a chemical reaction. That's your confirmation. If you were to end up with the same substances after the end of the process, that would indicate maybe you only went through a physical change. So any substance that we begin with at the beginning of this process we call a reactant. And any new substance that forms during the course of the reaction we call a product. Now, the reason that reactants and products differ from one another in a chemical reaction is that we've broken chemical bonds, potentially, and formed new chemical bonds to form new substances. So really what we're looking for is a rearrangement of the component atoms. The atoms are now rearranged in a new fashion where we now have a difference in the chemical bonding before and after the chemical reaction has occurred. So that's what we're looking for. Now, if we do have a chemical reaction, though, realize that we are following what we call the law of conservation of mass. What this states is that the amount of reactant atoms that we begin with are the same as the number of product atoms that we end up with. So we do not create or destroy atoms in a chemical reaction. We merely break chemical bonds, potentially rearrange atoms and form new chemical bonds. Those are the types of processes that may be occurring in some types of chemical reactions. But we have the same number of atoms before and after a chemical reaction. So if you count up the number of atoms you begin with before the reaction occurred, and you count the number of atoms that you end up with after the reaction has occurred, well then we should have the exact same number of atoms before and after the reaction. So the number of atoms and their identities are conserved in a chemical reaction. Now this is very critical in understanding how to balance correctly a chemical equation, which we'll follow up in our next tutorial. So please be aware of that relationship. Now, we're going to look at an example of this law of conservation of mass where we're retaining and conserving the number of atoms we begin with the number of atoms we end up with. So if I write a balanced chemical reaction for hydrogen gas combusting with oxygen gas to form water vapor, well, we can show what's called a molecular inventory to look at everything that we have, and then we can also relate this to an element inventory or an atom inventory to make sure that the number of atoms we begin with are the same as the number of atoms we ended up with. Now, if I want to show a molecular inventory, this will help me visualize when I have packets of 2 or more atoms present in my molecules or present in a formula unit for some types of reactions, let's say when there's an ionic species. And it will help me keep track of the number of atoms I begin with and the number of atoms I end up with visually. So I'm going to show you a little molecular inventory with some molecular models. I'm going to use white atoms to represent hydrogens, and I'm going to use red atoms in the molecular models here that we'll look at to represent oxygens. And we're going to look at a type of modeling that's called a ball and stick model, where we'll see atoms as balls, and the bonds between the atoms will be the sticks representing covalent bonds. If there's only one stick, like in the case of diatomic hydrogen, that indicates there's a single covalent bond. When we look at the diatomic oxygen molecule, we'll see two lines or sticks between the atoms, which will indicate a double covalent bond, which we'll be looking at later in the course in greater detail. Now, the coefficient in the front of my chemical formula indicates that I have multiple of that formula unit that's following it. So since I have diatomic hydrogen H2 here, but I have a coefficient, the number in front of 2, that indicates I actually have 2 diatomic hydrogen molecules. So each one of them contains 2 hydrogen atoms, so I could count 1, 2, 3, 4 hydrogen atoms total that I begin with. Now, since I don't have a coefficient shown in front of oxygen, that indicates a 1, and that would indicate that I have just one oxygen molecule that I'm looking at, and my oxygen molecule has 2 oxygen atoms present in the formula. So I have O2. As I'm looking at my products, I have a coefficient of 2 that's in front of my water molecules. If I draw a water molecule out, I have 2 hydrogens bonded to an oxygen in a bent molecule. Since I have a coefficient of 2, that indicates I should have 2 water molecules. So if I count up my number of atoms here, I have 4 hydrogens and 2 oxygens present. If I show my element inventory in this case, I can show the number of atoms. And so to show an element inventory, we don't have to draw out all the molecules, but oftentimes it will help students when they're first balancing chemical reactions if they look visually at all of the molecules that are represented by the chemical formulas in the balanced equation and relate that to the number of coefficients that they have. Now, in element inventory, what we're going to be showing is on the left-hand side the number of reactant atoms, and on the right-hand side we're going to show the number of product atoms. And right underneath the arrow, I'm going to label this EI for element inventory, and I'm going to list all the different types of atoms that I have present. So I have hydrogen atoms present and oxygen atoms present in my reactants and products. Now, if I'm following the law of conservation of mass, the number of atoms I begin with should be equal to the number of atoms I end up with. So I can look at this and I can see that I have 4 hydrogen atoms present to begin with because I have 2 diatomic hydrogen molecules. If you're having a hard time visualizing this, we'll realize we had those 2 diatomic hydrogen molecules that we visualized in the molecular inventory. So I had 1, 2, 3, 4 hydrogen atoms. I have 1 diatomic oxygen molecule, as we saw in the molecular inventory, that gives me 2 oxygen atoms. In my products, I have 2 water molecules, and I can see I've conserved mass. I have the same number of atoms before and after the chemical reaction because I have 1, 2, 3, 4 hydrogen atoms. I have 2 oxygen atoms present. Now, I don't always have to look back at the molecular model for determining my element inventory for conservation of my atoms. I can also just look at the chemical reaction and realize that my coefficient can be multiplied by any subscript to indicate the number of atoms I have present. So 2 times 2 gives me 4 hydrogen atoms. If there's no subscript shown, we assume it's a 1. We don't have to write the ones, and so if I take 2 times 1, that gives me 2 oxygen atoms, and so I can see that I have conserved. I begin with 4 hydrogen atoms, ended up with 4 hydrogen atoms. I started with 2 oxygen atoms, and I ended up with 2 oxygen atoms. Now, when I balance chemical reactions, we frequently will change the coefficients to ensure that we have conserved the number of atoms, but we never change the chemical formulas or the subscripts once we've identified our correct chemical compounds, because by changing the chemical formulas or the subscripts, we would indicate we have a completely different chemical compound that we're looking at. Now, let's consider some clues to try to tell in the laboratory if we have a chemical reaction occurring. So first of all, here's some observations we look for that may indicate a chemical reaction. If we see changes in color that are occurring, this could happen in a solution or this could happen in other states of matter, but frequently in the lab we'll be working with water-based solutions. But if I see a change in color, this may indicate a chemical reaction has occurred. I may have new substances that are producing the new color in solution. If I have a chemical reaction that is releasing energy in the form of light, that can indicate that we have a chemical reaction. We can also see energy changes in the form of heat energy transferred. We may see the formation of a new substance that's a solid, so we may get a precipitate that is coming out of solution, or we may be seeing smoke in the air, or we may see a metal coating occurring when we have a redox reaction, as we'll be talking about in this chapter. We may also see new compounds forming that are in the gas state. So we may be seeing bubbles produced in our solution that are not from a boiling process. That could be from a new compound forming. Or we may see fumes that we're observing in the gaseous state. Those could all indicate chemical reactions are occurring. We also may see, as I mentioned before, the absorption or release of heat energy. Now, this can sometimes also be accompanied with the production of light. We may see a flame occurring, such as when we're burning hydrocarbons such as methane or propane with some of our Bunsen burners, depending on where our lab is. And with respect to all of these different observations, these are very good observations that indicate we might have a chemical reaction occurring. If you see heat released, we have a special name for that. We call that an exothermic reaction. That means heat is going to the outside or going to the surroundings. That would include potentially heating up the glassware, heating up the lab bench. If you're holding the glassware, heating up your hand. Careful, highly exothermic reactions can actually potentially burn you, so you'll want to make sure your instructor has warned you if you have a highly exothermic process that might be occurring. Now, if you are absorbing heat from the surroundings, we call that an endothermic reaction. And if you were to actually hold that glassware, you would notice that your glassware starts to cool down as you absorb heat energy. Where that energy is coming from or going to is it's either coming from chemical bonds or being stored in new chemical bonds. And it's that difference in energy between the bonds we begin with in the reactants and the bonds that we end up forming in the products. That difference in energy determines whether or not we have an exothermic or an endothermic chemical reaction. Let's look at a few pictures of chemical reactions that could potentially occur in the lab and see if we can look for some of these observations or hints that a chemical reaction are occurring. So first of all, if we have elemental iodine being reacted with sodium iodide in the presence of starch, let's see what observations we might make that could indicate a chemical reaction could be occurring. As I add the elemental iodine, which is shown here as a yellowish color being dropped into solution, and I have my sodium iodide present as well in the solution that is occurring. The sodium iodide is actually the yellow color, and then we end up with elemental iodine that's actually the purple color here. Excuse me on the swapping the colors there for a second. What we can actually see happening is a color change that is indicated chemical reaction that is occurring here. If we take barium chloride solution, if we drop that into sodium sulfate, we can see there's an indication of a chemical reaction that's very easy to observe here because we see a precipitate forming in solution. It actually happens to be a barium sulfide white precipitate, but just to determine if I have a chemical reaction in the laboratory, I look for that change of state. My two solutions end up producing a solid precipitate, so it's a precipitation reaction. So that's something we can look for. If we take magnesium metal and we heat it up till it begins to combust with oxygen in the atmosphere, well, we can see an energy change. We see light energy being released in this process. We're also seeing fumes in the gas state that are being produced. These all indicate chemical reactions occurring. If you take a gas in your Bunsen burner, now some locations may be using methane as gas. On our campus here, we sometimes use propane as gas as well, but we have a hydrocarbon, meaning a compound that has carbon and hydrogen. That's a common type of fuel in our society. It's combusting with oxygen gas, and in this case, we can see again heat energy released in an exothermic process. We can see visible light energy released, so that change in energy in the emission of light or heat can often indicate a chemical reaction. This is an exothermic chemical reaction that we're looking at here. Now, if we take copper metal and put it in a solution of nitric acid, that indicates that we have a chemical reaction because we can actually observe quite a few indicators of a chemical reaction. The original nitric acid solution was clear and colorless. We start to produce a green colored solution. That color change indicates a chemical reaction. We also see gas bubbles forming from solution, and if we were to fill this glassware is heating up in an exothermic process. Those are all indicators that we have a chemical reaction occurring. We can also see that the copper begins to dissolve. So the copper starts to dissolve, and we no longer have metallic copper left. In fact, this green color in solution is resulting from copper ions forming as we start to lose electrons from the copper to form a new copper compound. We end up with copper 1 in copper 2 nitrate beginning to form. We also see a brownish yellow gas forming over the top of the solution. So as we start to see that color change in the gas state, indicates a new chemical reaction. We're starting to get nitrogen oxides released to the surrounding atmosphere. Those all indicate chemical reactions occurring. Those color changes can indicate that we have a rearrangement of atoms to form new substances with new colors. Also, the exothermic process indicates that we now have broken and formed new bonds where our resulting chemical bonds are lower in energy, and so we ended up with that excess energy being released to the surroundings in this exothermic reaction. Now, if we take calcium carbonate, okay, calcium carbonate will react with hydrochloric acid, and there's an indication this is occurring because the calcium carbonate, as it reacts with the hydrochloric acid in solution, will produce gas bubbles of carbon dioxide gas that evolve. So that production of gas bubbles indicates that there's a chemical reaction occurring. If I also were to fill the beaker, it doesn't feel warm enough to have been boiling, so I know that those aren't merely water vapor bubbles being produced from a boiling process. So I look for those types of different physical clues that I might have a chemical reaction. From here on forward in the course, I ask that you write down in your lab reports every time you see clues for a chemical reaction. Write down the observations you're observing, and if you can, especially as you get further into the course, please write down what you think are the names and or formulas of the chemical compounds that are forming as products that result in these observations that you can make in lab. So please be writing those down, and your lab instructor should be checking for those at every point in the course. Now, we may be asking ourselves, how do we really know if a chemical reaction has taken place? Well, first of all, we have to make sure we don't have a physical change. So if a substance is only going through a phase change, but we have the same identical substance in a new state of matter, maybe let's say we had an ice cube melting to form liquid water, or we're boiling liquid water to form water vapor. In all of those cases, the identity of the substance we had did not change. Its energy content definitely changed, but we still have water molecules, H2O molecules. In those cases, that is not a chemical change. That phase change from one state of matter to another for the same substance is a physical change, so it's not a chemical reaction. So we have to be very careful to not confuse those sometimes. Also realize mixing two substances does not always result in a chemical reaction. Oftentimes I will look for clues like we were looking at previously to indicate if there could be a chemical reaction that is occurring. Also, you will want to see if there's potentially just a mixture forming. So if you merely mix two or more substances together, that's just a physical change. Forming mixtures is not a chemical reaction unless we observe a change in the identity of the substance we begin with to new substances at the end of a chemical reaction. If we have the same substances before and after, we may have just formed a mixture. For example, if I take iron filings and I mix them with sand, well, they will not necessarily react, but I can tell this because I still have the original elemental iron, I still have the original silicon oxide in the sand, and we can separate mixtures by using only physical processes. So if I have a mixture, I can use a physical difference in their properties. Let's say I can use the magnetism of the iron filings we talked about to remove the iron and leave the sand behind. So if it only takes a physical process to separate out components of what I ended up with, that often indicates I formed only a physical change. I formed a mixture which could then be separated. If a chemical reaction were required to reobtain our original substances, then that would have indicated a chemical change must have occurred. We must have had new substances at the end of the process. So I have to be looking for that. So just realize, if you have a chemical reaction, you'll see some changes in the properties of substances because you will have new substances forming. If new substances are there after the end of the process, that indicates a chemical change has occurred. We look for our common types of indicators for chemical changes that we've talked about in this lecture, and we should continue to look for those in laboratory from this point forward. Okay, so it would be a perfect point after this tutorial to also watch our tutorial on balancing chemical reactions. So I highly recommend that you do that next.